Here we are. Let's do another one, very similar. So we get to find if there is an isomorphism. So again, since I've got all of the vertices labeled, I'm just going to put them here. And then here I'm going to put the edges. Oops, no, I'm sorry, I'm going to put the W's, right? The W's here. 1, 2, 3, and 4. Okay. So looking at vertex 1, it's got degree 1. So there's only one vertex of degree 1 on this, so it's got to be W4. All right, so let's look at V2. V2 is a vertex of degree 2. Well, that's got to be W3. And then vertex of degree 3 that's connected to a vertex of degree 2. So that's got to be the W2. And then that leaves V4 to be W1, and that does match, right? Degree 2 vertex. There it is. Okay, so then we get to go do the same thing for the edges. So E1, E2, E3, E4, V1, or F1. Yeah. F1, F2, F3, F4. And let's see, edge 1 here is between the vertex of degree 1 and vertex of degree 2. So that's got to be the F4. Then edge 2 has got to be between the vertex of degree 2 and the vertex of degree 3. So that's got to be F3. And then E3 and E4 are going to be both the F1 and the F2. So those would be like that. So there is an isomorphism. So if I start looking here, so let's find out how many vertices here. I've got V1, V2, V3, V4, and V5, right? 1, 3, that's a 3, 2. Oh, no, there's 5. Yes, there's, where's V1? Oh, V1, 2, 3, 4, 5 vertices. Okay, so how many vertices do we have over here that we're going to match them up with? So I've got, oh, well, you look at that. I can see 6. 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. Okay, so there's an invariant. They have not the same number of vertices. So that is not isomorphism. All right, so here we are. So now we have graphs just with the vertices labeled. And so you don't have to match the edges then. So let's just see if these two have are isomorphic. So let's see. Let's see if I got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So then we can go to edges. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. What about circuits? I see a circuit of length 3, right? 1, 2, 3. Actually, there's 2 circuits of length 3. Okay. So 2 circuits of length 3 in G. How about here in G prime? No. If I look at this, I have a circuit of length 4. Another 1, 2, 3, 4. It has circuits of length 4, not length 3. So that's the invariant. So it's not isomorphic. All right, how about this one? Okay, so if I start, so let's just count the vertices. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Same number of edges. Let's check it out. 1, 2, 3, 4, 5, 6, 7. So 1, 2. Mark them here. 1, 2, 3, 4, 5, 6, 7. Okay, same number of edges. So if I start, and I'm thinking about, this is one big circuit, right? Does this have one big circuit? Oh my goodness, I think it does, right? So it's one big circuit. So I think this can be expanded out. So I can match A, and I'll just choose the letter T. So A can go to T. And then the next vertex that's connected to A would be C. So C would go to U. And then it would go to the vertex E. So E would go to V. And then it would go to the vertex G. Oops. Whoa, come back. So then the vertex G would go to W. And then B, the vertex B would go to X. And then the vertex after B is D. D would go to Y. And then the last one, which is G, G would go to Z. Oh, wait a second. Wait, D, F. Oops, F is next. I missed one. Okay. So D to F. F goes to Z. And then F goes to A, right? The vertex A. Oh, and then we're back to T again. Okay, so that is one big circuit. So they are isomorphic. Isomorphic. So if you can make that one-to-one correspondence, it is isomorphic. Let's see about this one. Here I've got this. Oh, will you look at that? These are two triangles. It is not connected. So the graph G is not connected. And the graph of G prime is connected, and so that's our invariant. So we don't have an isomorphism.